My dear student, colleagues, and all the viewers who are watching this program live from Facebook page Physics Adda, I'd like to welcome you all to our International Physics webinar. And today it's our 63rd International Physics webinar. So, good afternoon to all here in Bangladesh, and a very good morning to all those who are watching this program live from UK. So, hope you are well and safe from Corona pandemic. So, we are passing a very bad time, and we need to adjust with this new normal situation, because due to Corona pandemic, we have to maintain some health issue, and due to Corona pandemic situation, we cannot continue our normal academic program inside the campus. So, we have to start online program. So our Department of Physics, Pabna University of Science and Technology, has started its online program, including online classes and online international physics webinar. And I'm happy to share with you all that we have already completed our 62nd international physics webinar. And in those international physics webinar, physicists from different countries are coming as a main speaker, and they are delivering their knowledge with our student. I think by this way, our students are benefited. And today is very important day for our department. But today I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Department of Gravitational Astrophysics and Cosmology, University of Glasgow, UK, in gravitational wave astronomy. And we have with us here today Dr. Martin Hendry, Professor Gravitational Astrophysics and Cosmology Department, University of Glasgow, UK, and he is connecting with us from UK through online. He has already connected with us, so I'd like to welcome our speaker. So, good afternoon, sir, and a very good morning to your part. And
hello, you're very welcome. I'm delighted to be here.
Yeah, it's my honor and privilege to host you, and welcome to my international physics webinar. Welcome to our university and country. And I think this is maybe your first collaborating program with any Bangladeshi university, sir. Isn't it, sir?
Yes, that's correct. Yeah.
Okay, great, sir. Thanks for accepting our invitation. And we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology. The main aim of our international physics webinar is to motivate and encourage our students in this Corona pandemic situation. So I think we are trying hard for this, and we have already completed our 62nd international webinar, and today it's our 63rd. So for those who are new, I'd like to inform that we have divided our international physics webinar into 3 parts. First of all, we'd like to introduce our speaker with all of you, and then our speaker will deliver his speech, and at the end we have a time. So in that time, anybody can join with us, and you may ask question by commenting also. So I think you may, if you have come to know the title of the today's international physics webinar, and title is the listening on Einstein universe, the dawn of gravitational wave astronomy, and our speaker is Dr. Martin Hendry, Professor Gravitational Astrophysics and Cosmology, University of Glasgow, UK. So he's a professor of gravitational astrophysics and cosmology in the School of Physics and Astronomy at the University of Glasgow, where he was first appointed as a faculty member in 1998. He's a member of the Institute of Gravitational Research and the Astronomy and Astrophysics Research Group, where he was a PDRA working in cosmology from 1996 to 1998, and where he also completed his PhD in 1992. He's a passionate enthusiastic for public engagement in science, and was a Science in Society Fellow for the Science and Technology Facilities Council, leading an international program of outreach with school and the public entitled the Exploring the Dark Side of the Universe. He's a fellow of the Institute of Physics from 2015 to 2017. He was a chair of the Institute of Physics in Scotland, and he's also was a head of that department. And in 2011, he was elected as a fellow of the Royal Society of Edinburgh in recognition of his contribution to research, teaching, and the public understanding of science. In January 2015, he was awarded a MBE for service to public engagement in service of Queen's New Year's Honours List. In 2015, he was also awarded the Royal Society of Edinburgh Senior Prize for Public Engagement. Research interests, his principal research interests lie in gravitational wave astronomy, particularly the use of future gravitational wave observation to constrain cosmological parameters and issues relating to the optimal combination of data from gravitational wave sources and their electromagnetic counterparts, to statistical methods for the analysis of cosmological dataset, particularly large-scale galaxy redshift and peculiar velocity surveys and survey of high redshift supernova. Third, application of gravitational lensing, including diagnosis of planetary and stellar atmospheres, circumstellar envelopes and the stellar winds, and lensing as a probe of the nature and distribution of the dark matter. And we can see his recent publication, and his Google Scholar ID. We can see his citation number is more than 44,000. So thanks all for all of your patience. It's very actually great things for our department, and I'm really feeling proud to hosting him in our international physical webinar. So thanks again, sir, for accepting our invitation. It's your time, sir. You can start your session, sir.
Thank you very much. You're very welcome. It's a real pleasure to be with you, and good day to everyone who's watching. I look forward to discussing some of the topics I'm going to describe in questions at the end. So I've called this talk Listening to Einstein's Universe, and we'll explain in a few minutes why we talk about listening rather than looking at or watching, because of course normally in astrophysics we observe the universe through light, but gravitational waves are a different way to study the universe. They are a completely different window with which to observe our universe. And I am a senior member of the LIGO scientific collaboration, which in 2015 made the first direct detection of gravitational waves. So partly what I'm here to do is to tell you the story of how we made that discovery and what it can tell us about the universe. But before I even do that, just a few more words about who I am. So thank you to Pretam for that wonderful introduction. But let me just emphasize that to be Professor of Gravitational Astrophysics and Cosmology means that I am interested in some of the biggest unanswered questions about the nature of our universe. We have a pretty good idea of how old our universe is. And in fact, the Big Bang Theory has become the standard description of how our universe began. And for about 100 years, we've understood that our universe is expanding. But why is it expanding? What was going on just after the Big Bang which drove that behavior? In particular, the expansion now appears to be accelerating. What is driving that? These are all questions where there are many gaps in our knowledge that we are trying to fill with the very latest astrophysical data. And that maybe is where gravitational wave astronomy might come in. We have grown accustomed to studying the universe with light, all the way from X-rays and gamma rays to radio waves, but gravitational waves gives us a new window on our universe, and maybe gravitational waves might just help us to answer some of these big questions about cosmology, about the nature of compact stars in the universe, and indeed the nature of gravity itself. And my role within the LIGO scientific collaboration, as well as being part of the team that carries out the scientific analyses, is also to chair our communications and education division. And that means that I'm responsible for coordinating our activities, attending science festivals, giving talks in schools, and giving talks in museums, organizing exhibitions about gravitational wave astronomy. And with the current global pandemic, we are changing our approach to that kind of outreach program, and more of our activities are being conducted online. So again, for that reason, I'm really delighted to be able to join you today online as part of that LIGO outreach program. So this talk is a lot about gravity. And before we get on to gravitational waves, let's really begin with our basic ideas about gravity. If you study physics at high school, you're typically introduced to the ideas of Isaac Newton. Sometimes it's in the context of a story of Newton sleeping under a tree and an apple falls on his head. We don't know if this really happened, but the story captures the idea that Newton was inspired by everyday things like falling apples to try to describe the mathematics that makes the apple fall. And his real genius was to realize that the same piece of mathematics could describe not just apples falling from trees, but the moon, for example, orbiting the Earth. And this was all described in the context of forces, which is a very fundamental part of how we learn physics at high school and indeed at university. We think of the forces between objects, and in the case of the gravitational force, Newton said that that exists between all massive objects in the universe. Now, about the turn of the 20th century, after Newton's ideas about gravity had reigned supreme for hundreds of years and had helped us to understand everything from the orbit of the moon around the Earth to the motion of stars within our galaxy, along comes Albert Einstein. And Albert Einstein had some deep questions about Newton's ideas of gravity. We can sum them up as follows. He asked essentially this question: how does the moon know that it's supposed to orbit the Earth? So Newton provides a mathematical framework in which the force of gravity is something we can calculate between massive bodies separated by some distance. But Einstein's problem with that was, how exactly does that force propagate across empty space? So this led, after many years, Einstein to develop his general theory of relativity. Firstly, he developed his special theory, which was all about how space and time look when you are traveling very fast. And the extension to general relativity was an extension that included the idea of accelerated motion. And there was a very deep principle underpinning that, which is that gravity and acceleration are actually equivalent to each other. Think how it feels when you're driving in a fast car. The car is accelerating hard along the road. You feel yourself pushed back into your chair, experiencing something analogous to what we feel, as Newton would call it, a force of gravity pulling us down due to the mass of the planet we stand on. So from this principle of equivalence, the equivalence of gravity and acceleration, Einstein rebuilt the whole notion of gravity entirely. And he replaced the notion of gravity as a force by gravity, and indeed acceleration, as a consequence of the curvature of space and time. So another scientist from around that time, a little later than Einstein, was called John Wheeler, and he summed up Einstein's general theory of relativity in the following phrase. He said that space-time tells matter how to move, and matter tells space-time how to curve. So the idea that's capturing is illustrated here by a simple picture. The picture is far from perfect. It misses out a lot of the detailed maths. Obviously, there's no equations on my slide. But what the picture at least conveys is this notion that what gravity does is to curve space-time. So we think of space-time as represented by the sheet of, well, like a stretched sheet of rubber, a bit like a trampoline, and the Earth is sitting on that, and it's causing a distortion in the grid of white lines. Excuse me. And that distortion means that objects passing close to the Earth will no longer follow a straight line. They'll follow a curved path. And that's the way that gravity manifests itself in Einstein's picture as the curved trajectories that massive bodies will follow in the gravitational field. So instead of thinking about a force, the objects are just following the natural curved contours of space-time in the vicinity of a massive body. Now, as I mentioned a little earlier, we've been accustomed over hundreds of years, really since the time of Galileo and Newton himself in the 17th century, to observe the universe in light. And in the 20th century, we expanded our observational window from just visible light to run all the way from radio to gamma rays, as I said before. So we can study the universe in all of these different forms of electromagnetic radiation. But what Einstein's general relativity does is predicts a whole new window in the cosmos in a new form of radiation called gravitational waves. So what exactly are gravitational waves? Well, 2 slides ago, we had that picture of the curving of space-time because of massive bodies being present in our universe. If those massive bodies are moving, then this will change the curvature of space-time, and it will produce ripples in space and time, which spread out through the universe, traveling at the speed of light, and that is what we call gravitational waves. Now, the complication is that these ripples are incredibly faint. So we had that picture of the Earth sitting on a stretched sheet of rubber. Of course, if you jump on a trampoline, the rubber bends a lot. But space-time, if we follow that analogy, is incredibly stiff, and it hardly bends at all, even when you have a massive object like a planet curving space-time. So if we want to detect gravitational waves that we could hope to measure, we need to disturb space-time a great deal. And we need to have, for example, 2 dense and compact stars orbiting very closely to each other. And that shakes up space-time enough that the ripples produced, well, perhaps we might hope to measure them. And that was the goal of the scientists working in my field for many decades. It was to design and to build and to operate a detector sensitive enough to detect those tiny ripples in space-time caused by violent cosmic events like the collision of 2 massive stars. The problem is, you see, that like ripples spreading on a pond, by the time gravitational waves reach us, they are much fainter because they're spreading out in all directions. And you can do the calculations based on Einstein's theory, and we had the prediction from that theory that in order to detect these space-time ripples, we would need to be able to measure movements less than about 1,000th the size of a proton, the elementary particle inside the nucleus of an atom. Or to put it in more everyday terms, if you take one of the hairs on your head, we had to be able to measure about 1 millionth the width of one of those hairs. Now that sounds incredibly challenging, and yet that's what we can now do. We now have instruments sensitive enough to detect those tiny changes. So LIGO, remember I said I'm part of the LIGO scientific collaboration. LIGO stands for Laser Interferometer Gravitational Wave Observatory. And there are 2 LIGO detectors, which are about 3,000 kilometers apart in the US. One is in Louisiana, that's shown in the top right, and the other is in Washington State, shown in the bottom left. And the way that these LIGO detectors work is that in the arms, which are about 4 kilometers long, laser light is sent back and forth along those arms, and the detectors are looking for changes in the interference pattern of those laser beams. So let's look at that in a bit more detail. So we have a laser beam that is split at the beam splitter. This is a simplified diagram of the optics within the LIGO detector, but it captures the essential details. So what you're seeing now is that as a gravitational wave passes by, it's shown in more exaggerated form on the right-hand side in a kind of cartoon. The gravitational wave will stretch and squeeze space-time so that the arms of the detector are made a little shorter and a little longer. And that pattern repeats itself as the gravitational wave sweeps past. So we can seek to measure that by looking for changes in the interference pattern of the laser light that goes along one arm and goes along the other arm. When the two laser beams are recombined after reflecting off mirrors at the ends of the arms, then we can look to see if the laser beams have moved out of step with each other. If they have, then that is a sign that the arm lengths have been changing. And that could be the sign of the passage of a gravitational wave. Now, the complication is that lots of other things can change the arm lengths as well. So we call these noise, a bit like doing a physics experiment in your undergraduate class, where there are certain measurements you make which can vary because aspects of your experiment are changing from one moment to the next. And the noise in our case comes from a whole variety of different sources. They're all listed here, and I don't have time to go into them in detail. But what this diagram is showing is the combined effect of those sources of noise. And it illustrates that our detectors are sensitive across a range of frequencies for the gravitational waves. That means how many cycles of the wave are passing us every second. And you can see the range. It's going from about 10 hertz to about 1000 hertz. And what this diagram is showing is that the sensitivity of our detectors is best somewhere in the middle, around a few hundred hertz. We measure that sensitivity using something called the strain, which is essentially telling us how small a change in the arm length we are capable of measuring. So remember that millionth the width of a human hair, that corresponds to a strain sensitivity of about 1 part in 10 to the minus, well, 1 part in 10 to the 23, which means 1 over 10 to the 23. So that's the challenge we have. We're trying to detect unbelievably tiny changes in the arm lengths, and yet all of these other sources of noise, apart from a gravitational wave, can produce those changes too. So it makes it very challenging to detect the signal over the noise. But we do have a big advantage because we know what that signal should look like. Or actually, I'm going to say should sound like. And that echoes back to my title, Listening to Einstein's Universe. Because if we just return to the previous slide for a moment, we'll see that the frequency range there actually corresponds to frequencies that the human ear can hear. So gravitational waves are not sound waves, but we can render them as sound waves so that we have a different way to interpret them. Yes, we can draw a picture, like on this slide, but we can also think of them as sound waves. And if they were sound waves, the pattern of sound they would produce is called a chirp. And that's what the diagram is also showing. It's showing a frequency that's increasing, and then it reaches a maximum, and then it fades away, it dissipates. And in the bottom left corner is a cartoon showing what is producing that chirp signal. This is the theoretically predicted signal you would get when two massive stars that we call black holes, so massive that even light cannot escape from them, if those black holes orbit around each other and then collide with each other and merge together to form one black hole, then the space-time disturbance that we expect is shown by the pattern in the graph, this chirp-like pattern. The frequency increases as the black holes get closer and closer together. It reaches a maximum. The strength of the distortion also increases, which is why the vertical extent of the graph is increasing too. And then once you have one black hole, it wobbles a little more, settles down, and then the signal fades. So that's the type of signal we were looking for. But as we said in the previous slide, there's a lot of noise. So our challenge is to hear a very faint signal against a loud background noise. And when I'm giving talks in high schools, I often use the following analogy to give a sense of how difficult that can be. Imagine you're in a crowded cafeteria in your high school. I suppose in the current pandemic, it's difficult to have to imagine this happening. But before all of that, and before social distancing, it would be, I imagine, very noisy in such a cafeteria. So you might imagine someone talking to their friend just on the other side of the table and struggling to hear them because there is so much background noise. That's basically the challenge that we have faced in trying to detect gravitational waves. How can you detect them above the noise? But knowing what the signal should sound like really helps. Just like if you're talking to your friend and you think you know what your friend is talking about, sometimes it's easier to work out what they're saying, even when there's a lot of background noise. So that's how we approach the analysis of our data. We compare our noisy data with predicted signals, and we try to find which one matches that noisy data best. But you also want to reduce the noise as much as you can. Imagine how much easier it would be in that cafeteria if one of the teachers suddenly says, "Be quiet, everyone." Shh. Then you could hear your friend very easily. So what we wanted to do over the last decade was to make our detectors more sensitive by reducing the background noise. And one of the ways that that was done was to make the mirrors at the ends of the arms shake a little less. So my group in Glasgow, not me, I'm an astrophysicist, but some of my colleagues that work on the materials technology of the detector, they made some really groundbreaking improvements to LIGO, leading for the UK our contribution to the global project to replace the mirrors at the ends of the arms with new mirrors, which were more massive, so they don't shake so much to begin with, and suspended on new silica fibers that shake even less. So this was called upgrading LIGO to advanced LIGO, and it was making the detectors sufficiently sensitive, or so we hoped, that they would be able to hear these signals, these gravitational wave signals, above the noise of the cosmos. And that's what happened. So what you're seeing here, I'm not sure if I'm sharing my sound, I hope I am, but it doesn't matter if I'm not. It almost proves the point I'm making, that maybe it's hard to hear the sound. If I'm not sharing it, it will be impossible. But we can still see the visual pattern of the chirp that we talked about a few minutes ago. And what is most important to note is that this chirp, let me freeze it so we can talk about it, but not there. There we go. This chirp was seen in both the LIGO Hanford and the LIGO Livingston detectors. Even though they were 3,000 kilometers apart, they appear to be seeing or hearing the same signal. So this was on September 14th, 2015, just over 5 years ago. And this was just a few days after the detectors had been switched on again, upgraded to advanced LIGO. So it appeared that the upgrades had worked. The detectors had become more sensitive, capable of detecting these chirp signals coming from deep in the universe. So what exactly had we detected? Well, it took us many months to analyze the data to be absolutely sure of what we had found. So we only announced this discovery in February of 2016, about 5 months later. But what we deduced from the data was that we had seen the final in spiral, spiraling in towards each other, the merger, and then the ring down. That's where a single black hole just wobbles some more and then settles down. Those 3 stages of a pair of massive black holes more than 1 billion light years from the Earth. So the in spiral had probably been going on for millions of years, but with a very much lower frequency. And it's only during the final fraction of a second before the merger that the frequency had increased enough to be audible to our LIGO detectors. And then we saw the merger, and then with now a more massive single black hole, it rings down, space-time settles back down again, and the signal is over. So this remarkable detector sensitivity had allowed us to hear these final moments of the death spiral of these two massive black holes. And here's an animation inspired by the real data, so matching the characteristics of the actual event of that final dance of the black holes around each other. So as they merge, a burst of gravitational waves is released, and that is just imagined by the red spike shown in the animation. Let's watch it one more time. So all of this was unfolding in just a fraction of a second. And in fact, the mass of the two black holes before they merged totaled about 65 times the mass of the sun. We'll look at something in this slide which will show us that. So here's the waveforms on the left, and there's the chirp-like pattern that we've been talking about. And here is a graph from our discovery paper showing our estimation of the mass of the first black hole and the mass of the other one. And both were around 30 times the mass of our sun, one about 36, the other about 29. Now, with some uncertainty, which is what this blob here is indicating, that there is an uncertainty in the measurement of the mass. But we also could estimate the mass of the final black hole after the merger had taken place. And that was only 62 times the mass of the sun. So what this told us was that in just a fraction of a second, the equivalent of 3 times the mass of the sun, or about 6 million kilograms, had been converted into energy, gravitational wave energy, according to Einstein's famous equation, E equals mc squared. And if all of that happened in just a fraction of a second, we could estimate the power in gravitational waves associated with that. We take the energy, we divide by the time taken for that gravitational wave burst to occur. Let's just watch the video one more time. What we're basically doing is trying to estimate how much gravitational wave power is emitted when we see that red spike. It's not really red, of course, it's gravitational waves. It doesn't have a color, but the red is just to, in the context of the animation, to highlight the moment when most of that energy is emitted. And because it happened in a very short time, the power was enormous. In fact, it was more luminous in gravitational waves than about 50 times the luminosity in light of every star in every galaxy in the entire universe. But it was over in just a fraction of a second, and then space-time settled down again. So this was our very first gravitational wave event. It was a breakthrough discovery for fundamental physics. The discovery was awarded the Nobel Prize to 3 of our senior LIGO scientists in 2017. But it was really just the beginning, because also in 2017, a third gravitational wave detector began operations at this advanced sensitivity. This one is called Advanced Virgo, and these are our partner collaboration. They well, the Virgo detector is based in Italy, but the Virgo collaboration involves many European countries. And the great advantage of having 3 detectors was that we could now determine on the sky the direction from where the gravitational waves came with much greater precision. When it was just LIGO Hanford and LIGO Livingston, then pinning down the direction of the gravitational waves is tough. It's based on the time delay between the signal arriving at one detector and the other. But there's a whole ring of positions on the sky that would all have the same time delay. So you don't know for sure which part of that ring the signal really came from. But once we had 3 detectors operating, then you have 3 rings for each pair of detectors, and where the rings overlap, that's where the signal must have come from. So in fact, within just 2 weeks of Virgo beginning operation, we already began to see the benefit of having 3 detectors. Because look at this one. This was a black hole binary observed on the 14th of August, 2017. And we can see that it's much better localized on the sky to about 60 square degrees compared with the earlier detections made by just LIGO, Hanford and Livingston, where the sky area was much greater, more like 600 or even 900 square degrees. So having 3 detectors was great for spotting where on the sky the gravitational waves came from, and that gave us the chance to look for electromagnetic signals from the same source. Now, in the case of black holes merging, we don't generally think that they will give off any electromagnetic radiation. But there's another type of compact object called a neutron star. And when 2 neutron stars merge, well, something like this happens. So what we see is the chirp from 2 neutron stars merging, but the pattern is different now. It sweeps up very rapidly at the end, and it reaches a higher frequency than the black holes. That immediately tells us that they're less massive than black holes. And neutron stars, they can have masses of about up to 2 times the mass of the sun, we think. And when they collide, astronomers had long believed that what can also happen is the release of a burst of gamma rays from an event that we call, surprisingly enough, a gamma ray burst. So what you see at the top, let's play the video again, is the gamma ray signal detected by the Fermi gamma ray satellite that was observed about 1.7 seconds later than the gravitational wave signal that LIGO and Virgo detected. So what we think was going on there is that as these neutron stars were spiraling in to collide, producing gravitational waves that we detected with LIGO and Virgo, at the same time, a gamma ray burst was being created. Now, there's a very short time delay, 1.7 seconds, before the gamma ray signal begins, but all the way across the universe from where the signal was emitted, we think it was emitted from about 130 million light years away. The gamma rays and the gravitational waves, this now suggests, were both traveling at the speed of light, just like Einstein's theory predicts. So the gamma rays arrived only 1.7 seconds later than the gravitational waves because we think they were emitted 1.7 seconds later. So this is very firm evidence that gravitational waves do indeed travel at the speed of light. And what this allowed us to do was to look for the signal in light, in visible light, not just gamma rays. So the sky localization from the gravitational wave detection was really quite precise, and that allowed us to identify that this little galaxy here was where the gravitational wave event had come from. And within just a few hours, astronomers using optical telescopes had studied that galaxy and found a new star, the star that was left over after the neutron stars merged. We call it a kilonova, and it's a really rich source of information about all sorts of areas of astrophysics, about the condition of matter inside neutron stars under extreme conditions, and also the formation of some of the heavy elements. But before we get to that, let's say a few words about the area that I was directly involved in, which was using this kilonova, the remnant of the neutron star merger, to estimate how fast the universe is expanding. So I mentioned before that we've known our universe is expanding for about 100 years, but measuring precisely how fast has proven difficult to achieve. So the original idea of an expanding universe, we now recognize Edwin Hubble and Georges Lemaitre as the scientists who really proposed this. Hubble made observations that helped to confirm the theoretical ideas of Lemaitre and ultimately of Einstein himself. And well, this expansion rate we usually call the Hubble constant, and measuring it is quite challenging. And what you see on this graph is some bands. You see a green and an orange band, and those denote different values of the Hubble constant and their uncertainties that have been measured by different methods using light, and they don't agree with each other. And that is a real puzzle for cosmology. I think you're getting another webinar very soon from the Nobel laureate Jim Peebles, who is a wonderful scientist and one of the leading cosmologists of the last 40 years. And Jim, I'm sure, will talk a little more about this, about the big puzzle we have of why the Hubble constant we measure one way doesn't agree with the Hubble constant that we measure in other ways. But what happened in 2017 was that now we had another way to do it that didn't use light at all. It used gravitational waves to tell us the distance to the galaxy where the kilonova occurred. Now, we still need to use light to measure the other property that's called the redshift so that we can determine how fast the universe is expanding. But what the curve shows is our estimate of the Hubble constant. Now, from only one event, actually, our estimate isn't terribly good. That's why the curve is broad. And in fact, our result is consistent with both the green values and the orange values. So we can't really say which of them is the correct one. But we hope in the future to be observing many, many more of these neutron star collisions. And that will help us to work out, perhaps, what's really going on with this Hubble constant and the expansion of the universe. Now, I'm nearly finished, but I mentioned that the kilonova left behind by the neutron stars merging has been a rich source of information about many areas of astrophysics. And another one is the mechanisms by which the heaviest chemical elements can be formed. The density created in the environment of the kilonova forming, the neutron stars merging, is so extreme that it's a good environment to make gold and platinum and silver. So we now see in this periodic table that the category merging neutron stars as the origin of the chemical elements, it now is believed to explain a lot of the very heaviest elements. So the gold in my wedding ring probably came from the merger of neutron stars billions of years ago. Now, we've detected many more black hole mergers also. Here's a little cartoon showing some of them. So they're spiraling in towards each other and they're going to merge. And that's, in a sense, the state we're now in. That yes, of course, the individual events are interesting in themselves, but we are actually moving towards being able to study the population of events and to see what that tells us about how things like black holes formed, and also to test gravity itself. So here's a rather complicated looking graph, a pair of graphs, but let me just emphasize a couple of points here. What you're seeing is a graph that shows two different aspects of analyzing the gravitational waveforms. So remember we talked about them spiraling in towards each other and then merging and then having this ring down, this final phase. So we can estimate the final mass of the black hole in two ways. We can estimate it directly from the ring down, or we can measure the initial masses of the two black holes from the in-spiral and then predict what the final mass should be if general relativity is correct. Now, if general relativity is correct, then those two methods should give the same answer. So what this graph is showing is the answer to the question, do they give the same answer? It's showing the fractional difference between the final mass worked out one way and the final mass worked out the other. So if general relativity is correct, all of these should be zero. But of course, our measurements have errors and uncertainties and noise, so we don't expect to get exactly zero every time. But what we see reassuringly is that the combination of all the different gravitational wave events analysed together is clustered quite tightly around zero, reassuring us that general relativity is passing the test. And the other axis is just another aspect called the spin of the gravitational wave signal, which again, we can test in different ways, checking whether general relativity is correct. And the right-hand plot does something similar. It looks at different mathematical expressions that kind of expand the predicted waveform in a mathematical series of terms. And if general relativity is correct, then we expect that really all of those terms should be close to zero. And what's reassuring to see is that they are. And what's also reassuring to see is that when we look at all the sources together, that's the combined signal from all of the black holes analysed together, then we get much better constraints than if we just consider them individually. So that's the power of having a population of detections to look at rather than just one. So what I'm talking about here is our first catalogue of gravitational wave sources. And this was published in December 2018, and it comprised 10 binary black hole mergers and 1 neutron star merger. And the bottom line is that from analysing all of that, Einstein was pretty happy because Einstein's general relativity seems to be consistent with what we observe. Now, the good news is that we've been detecting many more candidate events since then. And in just a few weeks' time, we expect to publish our new catalogue with many more sources. So I can't share those results with you this morning, but watch the news because they're going to be published quite soon. So what has been happening since December 2018? So my final few minutes, I just want to say a little about that. Well, in 2017, once the neutron star merger had been observed in August, actually the detectors stopped taking data and we began a process of upgrading them even more to make them more sensitive. So that involved a lot of work, but it was completed, ready to begin operations again on April 1st, 2019. And that was what we called O3, our third observing run. And our Virgo colleagues, they were ready to begin operations at that time as well. So during our third observing run, O3, we saw many more events. We saw, if you combine with O1 and O2, a total of 60 candidate events so far. And look at how the rate of detection of events was steeper during O3. O3 was divided into two parts, one from April through to October, or September, and then one from November through to March of 2020. We had to stop a few weeks early because of the pandemic, but it was always planned that we would stop again and upgrade again. So the next observing run 04, scheduled for 2022 probably, will be even more sensitive. We might be detecting gravitational wave events every day. So that's something to look forward to. But even from O3, we already have some major successes to report. And the other big difference for O3 was that we begun sending out alerts immediately. So that was to give astronomers the best possible chance to use telescopes across the spectrum of light to look for electromagnetic counterparts of our gravitational wave sources. And all of that was happening in a way that the public could share with as well. So this website here, during our third observing run, we would update the events within minutes of the gravitational wave candidate being detected. And there was also an app that you could download for free, which would allow those alerts to be sent to your phone or to your computer. Now remember, these were just candidates. It was always going to take us a few months to do the careful analysis to confirm if it was a real event or just noise. But we wanted to make sure that at least we told astronomers that it was a candidate event so that we didn't miss the chance to detect an electromagnetic counterpart. Now, the bad news is that throughout '03, we didn't detect any electromagnetic counterparts, or none that we are sure about. And the main reason for that is that most of the events that we detected are very much more distant than the neutron star merger that we talked about in August 2017. For example, we detected another neutron star merger on April 25th of 2019, and we announced this one in January 2020. And this, we think, is more massive than any binary neutron star pair that we've observed in our galaxy. So that's what this graph is trying to show. So this is a graph showing the masses of pairs of neutron stars within our galaxy. We can observe them using radio waves. We don't detect gravitational waves from them, but we know about them, and they tell us a lot about general relativity as well. But our binary neutron star pair had a mass, a combined mass of at least 3.25 times the mass of the Sun. The precise mass depends a little bit on what we assume about the spin of the neutron stars. So we could get a quite narrow prediction, but maybe that's not quite correct. So we have to allow that the mass could be even greater, as shown by this blue curve. But in fact, that would be even more surprising if this pair of neutron stars had a mass as large as 3.75 or 4 times the mass of the Sun. The bottom line is this newly discovered pair from 25th of April last year looks substantially different from the neutron star pairs that we observe in our galaxy. So straight away, that's telling us that there's interesting things going on, that maybe gravitational waves are letting us study that radio waves were missing, were not detecting. Now, this signal was much weaker than the signal that we saw in August 2017. And the chirp waveform, well, I'm showing it with the signal and without the signal, and you can probably barely notice the difference, but let's help a little bit. That's essentially me tracing out the pattern of the chirp. So it's got the same basic pattern as the one we saw in 2017, but much fainter and much harder for our algorithms to detect. But we've also seen a number of interesting black hole mergers. One that was detected on April 12th of 2019, we announced that in April 2020. And this was a pair of black holes with quite unequal masses, with one of them several times more massive than the other. And what that does is it changes subtly the gravitational wave signal. It means that it doesn't just have a simple description in terms of what's called the lowest order harmonic or multipole, but it needs extra harmonics, a bit like playing a musical note on a piano. If you play the musical note on a piano, what you're getting is frequencies that correspond to the main frequency of the note, but you also get overtones, you get harmonics that make a nice sound. And essentially, events where the masses of the black holes are not so equal, they produce a more harmonious sound when we listen for them than just having equal mass black holes. And that extra information that we get allows us to work out, for example, the distance to the black holes rather more precisely than if we just use the dominant multipole, like the main frequency of the musical note, to use that analogy again. Almost done, just 2 more events to mention. Another one that was detected in 14th of August 2019, we announced this in June of 2020, and this one is a little bit of a mystery. It's another event where you have a very massive black hole and a much less massive companion, but that companion seems to be too massive to be a neutron star, but not quite massive enough to be a black hole. So we're honestly not sure which it is. It's in what we call the mass gap between previously what we believed were the most massive neutron stars, even more massive than the one we talked about in 25th of April, and less massive than the least massive black holes. So this mystery object, well, again, if it is a black hole, then it will produce these higher harmonics, very interesting structure in the signal because of the difference in mass between the very massive one and the less massive one. But we're not actually sure that it is a black hole. It could be a neutron star, but it would then be the most massive neutron star by far that has ever been detected. So studying of this event will continue for, I think, many years to try to really fully understand it. And of course, what would be even better is if we can observe more events like that, and we'll learn from the population of them what's really going on. Now, the final new event to tell you about, we just announced in early September. And this one was detected on the 21st of May of 2019. And let me play a little animation. And we believe that this was two very massive black holes. So in that sense, a well understood collision. But because they were so massive, we only saw a tiny part of the signal. We only saw this part down here. But that was enough to tell us that the black hole left behind was probably about 150 times the mass of the sun, more precisely about 142 times the mass of the sun. And that makes it the most massive black hole that we've discovered with gravitational waves. It makes it actually what we call an intermediate mass black hole. And it's so massive that we think it's probably unlikely that it was formed from black holes that were the product of a massive star going supernova, collapsing, and forming a black hole. Because the bottom line is the two stars that formed a really massive one, our monster black hole, we think had masses of 66 times the mass of the sun and 85 times the mass of the sun. And those are too massive to be formed directly from a collapsing star. So what we maybe are seeing is a kind of hierarchical family of black hole mergers. So less massive black holes merged together. We didn't detect that, but in the past they merged together to form this one and this one. And then the merger of these two, we did detect to leave behind this intermediate mass black hole, which is the biggest ever. So understanding these sorts of events might help us to piece together the picture of exactly how black holes form into the supermassive black holes that we have at the hearts of galaxies. So what happens next? Our detectors are being upgraded again. Now that's going to take a while because of the pandemic. We have to put safety first, but we are still hoping to begin operations in about 2022. And in fact, just a few years after that, there will be a third LIGO detector will come online in India. So it's beginning the planning and construction phase now. And before even that, there will be a detector operating in Japan called Kagra. And the big advantage of having more and more detectors is that we can localize on the sky even more precisely where the gravitational waves came from. So within a few years, we hope to be detecting as much as one event per day and to be determining the sky positions well enough that finding the counterparts in light will be a whole lot easier. And that hopefully means that we'll be detecting many more binary neutron stars that we can use to measure the Hubble constant and the expansion of the universe, and binary black holes to help us understand the origin and evolution of black holes in our universe. So we think that gravitational wave astronomy has a very bright future, and that includes this fantastically exciting development that LIGO India will begin operating in just a few years. So I hope that you've enjoyed hearing about this amazing story of the past 5 years and the first detections of gravitational waves. But I hope I've also conveyed that this new field of gravitational wave astronomy also has a very, very bright future. Thank you very much.
Thank you, sir, for your wonderful presentation. And I think students have learned a lot of things about gravitational waves and LIGO. So if you allow, we can start our discussion session. We have got some question. So the first question I can add in the screen. So is gravitational wave produces only due to merging the two black holes or two neutron stars? Is there other sources of gravitational wave?
That's a really great question. And in fact, I was hoping someone might ask that because it lets me expand a little bit on some of the ideas I discussed. So we talked about space-time being very stiff when we tried to draw the analogy with a trampoline. And that means we need very massive objects to be moving very fast to shake space-time enough to produce a gravitational wave signal. So colliding neutron stars and black holes are really good for that because they're very dense and they can orbit very fast, close to the speed of light, very close together. But in principle, any moving mass can produce gravitational waves. So if I shake my fist, I'm producing gravitational waves, but they're incredibly weak. You know, we couldn't ever hope to detect them. So that's why the events we've detected so far have been from the collisions of compact massive stars, because those produce really strong signals. But there are other sorts of astrophysical events that could produce gravitational waves. For example, if you have a single neutron star that is not perfectly spherical but has a bump on its surface and it's spinning fast, that would produce gravitational waves. We're searching for that too, but we haven't detected any yet. But we hope with the upgrades in our fourth observing run that might be possible. And in fact, the other possible source of gravitational waves is the Big Bang itself. There could be gravitational waves left over from the violent expansion of the universe in its earliest moments. Again, would LIGO be able to detect those? We're not sure, but we're certainly searching for them all the same. Thank you. Great question.
Yeah, thank you, sir. We have another question. So how to detect the primordial gravitational waves of inflation?
Yeah, that's leading on perfectly from my last remark. So in fact, actually, to detect the primordial gravitational waves from inflation is especially challenging for LIGO and Virgo. And the reason is that those gravitational waves, we believe they exist because we think inflation is a good theory to describe the expansion. But as the universe has continued to expand, those gravitational waves will be redshifted, they will be stretched. So that means that even if they did exist, as we think they did, then their wavelength nowadays will be so long that it would be very difficult for LIGO and Virgo to detect them. Their frequency, in other words, would typically be outside the sensitivity range of LIGO and Virgo. So the much better way to detect primordial gravitational waves from inflation is to look at the indirect effects they had on the cosmic background radiation. Now, maybe Professor Peebles will talk about this in his webinar, or if you like, I could, do another one sometime in the future to talk about this. But that's a different way to detect gravitational waves, and it's by looking for what we call the polarization of the cosmic background radiation. And a few years ago, in 2014, there was a claim that we had detected such a signal, but it turned out just to be noise. And that's a good illustration of just how hard it is to do this. In fact, when we made our announcement in 2016, we were thinking a little about that. We were thinking, will people believe us? Will they say it's just noise again, like the cosmic background radiation claim? So that made us really incredibly careful and cautious before we announced our detection. But I'm very confident that in the future, we will detect those primordial gravitational waves using cosmic background radiation. It's just hard, and the astronomers that work on that really, they deserve our patience because they are facing a real challenge to make measurements.
Thank you, sir. We have another question. So can neutron star live forever or decay after some time?
There's a number of ways to look at that. The neutron stars, firstly, if they're spinning, then that spin will slow down. That we see evidence for this in neutron stars, which are very young, that yeah, they spin incredibly rapidly at the beginning, just soon after they are formed, but we see evidence that they slow down. So if you could wait long enough, then yes, the neutron star spin would slow down and stop. In addition, the neutron stars are typically very hot. And the reason for this is as they collapse, as the massive star collapses, it releases a lot of gravitational potential energy. And that, firstly, combined with the conservation of angular momentum, explains why they spin so fast, and it also explains why they are so hot. So we can detect neutron stars in X-rays and gamma rays, but again, if you wait long enough, they would cool down. And if you wait even longer, then eventually, if our theories of particle physics are correct, we think that probably even the fundamental particles like protons might decay. But the timescales for all of that to happen are unimaginably long, 10 to the 100 years or more. So to all intents and purposes, the neutron stars stick around for a long time before any of that happens. So we can think of them as living for a very long time.
Thank you, sir, for your answer. So we have another question. What are the possible application of gravitational waves? So can we make any instrument using gravity waves in future?
Again, a really great question. There's a number of ways to answer that. Let me give a very short answer, which is we don't know. And that's probably the most honest answer I can give, because if you look at the history of science, there's often been fundamental discoveries which led to applications that no one imagined. And therefore, maybe that will happen with gravitational waves. We don't know. But I think, again, we need to be a little bit cautious. And there's an interesting story to tell where we compare gravitational waves with electromagnetic waves. So a physicist from my country, James Clerk Maxwell, he predicted electromagnetic waves in 1865, actually in a series of papers, but the big paper was published in 1865. And remarkably, it was only a few decades after that before physicists were able to produce electromagnetic waves in the lab. That's what gave us radio, and then much later television, microwaves, all of our modern technology. So electromagnetic waves were predicted theoretically, and then we could produce them just a few decades later. In the case of gravitational waves, we have no idea how to produce them. Well, actually, we do. We produce them by making two black holes collide. But how do you do that in your laboratory? You can't carry a black hole around in your pocket. So being able to produce electromagnetic waves is comparatively easy. Being able to produce gravitational waves might be impossible. And if it really is impossible, then it's hard to imagine what technological applications there might be. If we could somehow do it, then you could manipulate gravity, and you could have things like hoverboards that you get in sci-fi films. If you've seen Back to the Future, for example, he has his hoverboard. I would love to have one of those, but we don't know how to manipulate gravity to make it possible. Maybe, just maybe, gravitational waves will help us do that. So what I'm really saying is that the direct applications of gravitational waves themselves are a complete mystery. We don't know what those might be. But there are already many, many applications of the technology we need to detect them. I said at the beginning that we need incredible sensitivity to detect these signals, measuring a millionth the width of a hair. So that precision has driven the technology of our lasers, our material science, our vacuum systems in the arms of the detector. And there's been lots of spin-off technology associated with that. Everything from control systems for lasers that is used in eye surgery or medical applications, through to materials that are incredibly strong adhesives, just like we need very strong adhesives to glue the mirrors to the cables that suspend them, the fibers. Those same adhesives have been used for high performance supercars. So that's a rather, specialized application, but across a wide range of commercial and medical and technological applications, our detector technology is already bearing some fruit. So that was a long answer. Apologies for that, but it was such a good question, and I think it deserves to think about in these different ways. Let me just echo again, I would love to believe that there are direct applications of gravitational waves. We just don't know they are yet. And maybe someone watching this morning will be the scientist that discovers that.
Thank you, sir, for your nice answer. So we have another question. So when you were describing how the waves move through space-time, is it like taking a heavy hammer to a sheet of metal in terms of how it moves?
That's again a lovely question. Yes and no. These questions are quite subtle. They rarely have a straightforward answer. So in the sense that we can think of a heavy hammer and you hit a bell and then the sound propagates through the metal, there are some similarities there because gravitational waves are propagating through the fabric of space-time itself. But the difference is, the important difference is that sound waves propagating through a solid body are longitudinal waves. So they are compressions and stretching of the body, which are in the direction of the motion of the wave. So in undergraduate physics programs, you learn about the properties of waves in general. So maybe the students have heard of this already, longitudinal waves. Gravitational waves are transverse waves. So the disturbance is transverse to the direction of propagation. I won't go back to the slide, but near the beginning, we had this slide showing the stretching, squeezing of space-time. So that was for a gravitational wave coming directly out of the screen. Well, maybe we shall go back. It might not just take a moment. You get the talk in reverse. The arrow of time is reversing. We just need to wait for almost there. I went too far. So let me just very quickly find it and then I can make that point again. Here we are. So this cartoon showing the stretching and squeezing of the arms is corresponding to what would happen if a gravitational wave were coming directly from the screen towards you. Now, because we have multiple detectors which are pointing in different directions on the surface of the Earth, that means that they will have different sensitivities to a signal coming from a particular direction. So that's how, using that information and the arrival time information, that is how we can work out where the signal came from. So it's using this transverse property. So yes, bottom line is, it's a little bit like ringing a bell. That's why we call the final part of the waveform the ring down. But the crucial difference is the ringing of a bell produces a longitudinal sound wave. This produces a transverse wave.
Thank you, sir. There is another question. So are there any neutrino signal associated with mergers producing gravitational waves?
I'm sorry, could you say that again?
So
any new?
Are there any neutrino signals associated with mergers?
Okay. Yeah, sure, excellent. No, there's been no confirmation of that so far. We would love that to happen. Now, for example, in the summer of 2018, there was an announcement of the first simultaneous detection of neutrinos and light, and it was coming from an active galactic nucleus, and this was a big deal. It was announced by the National Science Foundation in July 2018. But when that signal was emitted, our detectors, I think they weren't operating at that time, when the signal was detected in light and in neutrinos. But we still very regularly do share our alerts with the neutrino observatories. So there's IceCube, there's other detectors around the world, and we are just waiting for when we might get a combined gravitational wave, light, and neutrino signal. And one of the ways we might get that is from a supernova explosion, because a supernova could produce gravitational waves that we might detect if the supernova happened within our galaxy. So if that did happen, and we were lucky enough to observe it, then we really would seriously expect that there could be a neutrino and a gravitational wave and a light signal all combined.
Thank you, sir. So we have another question. So can trinary or higher number of mergers possible for gravitational wave production?
I just again missed the beginning of the question. Sorry. Can trinary? Oh, yeah, understood. Yeah, absolutely. Well, that's a great question too. I wonder if I might just go to one of my slides again. Could I do that?
Yeah, of course.
Thank you. So let's just show. Well, let's show the big movie. This one. So what this is showing, let's just start it again, is the final merger of two black holes. Now, what you should notice is the time in the corner. I didn't talk about that very much, but I mentioned that the event happened in just a fraction of a second. So the gravitational waves only became powerful enough for us to measure during the final 1/3 of a second before the merger. So the short answer now to the question, or maybe not so short, but the kind of basic answer is that yes, trinary mergers could happen, but the complication is we would only detect the black hole signal during the final moments before the merger. So it is very unlikely that all three of them would collide at exactly the same time. What you would probably find instead is that two of them would collide first, and then the merged black hole would collide with another one. And that's very much like what we think may have happened in this one from 21st May of last year. So, yeah, this one. So the cartoon shown here is illustrating that. Now, the point is, we don't know how long of a gap there was, if this really is what happened, between this merger, and then the one that we detected. So you could maybe regard that as like a trinary or a quadrinary, I think you would say, involving 4 black holes. But we only saw the final part. But once we have more sensitive detectors in the future, I included a couple of extra slides just in case someone asked me this. In the future, we will have a spaceborne detector called LISA that will be very sensitive to much lower frequency signals that couldn't be detected on Earth. And those will come from much more massive black holes. So a definite scenario that's possible is that 2 less massive black holes would merge together, and LIGO and Virgo would detect those, but then that merged black hole would collide with a supermassive black hole, and LISA would see that. So you would need instruments across the whole gravitational wave spectrum to tell the full story.
Thank you, sir, for your nice answer. So we have another question. So could this heavy neutron star be a dark matter object?
We honestly don't know. We think probably not, because much of what we understand about dark matter suggests that it doesn't clump together. And if it did, then there would be ways we could test for that. We could look at stars in nearby galaxies and look to see if they temporarily got brighter when one of these dark matter stars passed between us and the background star. This is a phenomenon that we call gravitational lensing, or gravitational microlensing. And yes, we see gravitational microlensing, but it doesn't seem to happen often enough to suggest that all of the dark matter is in that form of clumpy objects. So we would call such dark matter machos, massive compact halo objects. And we don't think there are enough lensing events to suggest all of the dark matter is machos. So it's definitely interesting that we're finding an even more massive star. Maybe it isn't a neutron star, maybe it's something more exotic. For example, a quark star has been suggested. but we don't think it could be made of dark matter particles because we think those are too diffuse to ever clump together as much as you would need for something like our neutron star or maybe neutron star.
Thank you, sir. So we have another question. So why it is very weak? Is this an indirect evidence of graviton?
Now that's a great question too. I mean, the reason that gravity is so weak can indeed be thought about in that framework. So the other forces that, were kind of unified in quantum electrodynamics, that's the interaction that we call the strong interaction. There's also the weak nuclear interaction, and there's electromagnetism. So we believe that if you consider what the universe was like in its earliest moments, then the differences between these interactions become less and less important, that they kind of unify into a single interaction. And it's only as the universe expanded and cooled that the interactions looked different from each other. Now, our goal, our dream, is to unify gravity also into that picture. And essentially that would involve quantizing gravity. So the person asking the question clearly knows about this, and that we have suggested that the particle associated with the gravitational interaction, the gravitational field, when we quantize that field, that we would call it the graviton. So absolutely. So now, that was just some context for those maybe less familiar with ideas about gravitons. What does our data say about all of that? Well, to be honest, not very much yet, because we are probing gravitational fields in the strong regime, as we call it, but not quite strong enough to be really testing quantum gravity. But there's another way round you can look at it. Remember I said that Einstein was really happy that he passed the test because the tests of GR that we carried out were all consistent with our data. So the tests that we carried out were all classical GR. That means without quantum effects. And there's one version of our test, which is to suppose that the graviton does exist. I mean, we believe it does exist. It's just that we're not seeing its effects yet. But to imagine, suppose the graviton was much more massive. We think it's actually massless. But if it had mass, then its effects would be much more noticeable. And what we've been able to do is to put limits on how massive the graviton would be allowed to be. Because if it was more massive than that, we would see the effects already in the gravitational wave signals. So the question is a really perceptive one, that already, even though we haven't detected gravitons, we can learn something about their properties because we don't see any effects of gravitons. And actually, sometimes in science, we make a lot of progress that way by ruling things out, by looking for an effect. And if we don't see it, deducing that something must be true. So the graviton cannot be very massive. And if it does exist, we think it does, then we will need much more powerful gravitational wave detectors before we can really see direct evidence for it. But watch this space, it's going to happen.
Thank you, sir, for your nice answer. So we have another question. So can we gauge gravitational wave of dark matter halos?
Again, a nice question that links back to one of the earlier ones. Remember I said that we don't think dark matter clumps together very much. So if it doesn't, then that means it's not likely to be dense enough to produce gravitational wave signals. However, if gravitational waves are produced by something else, something more conventional, like a bunch of black holes merging, like in our catalogue, then as those gravitational waves spread out through the universe, eventually observed by us, maybe they have passed through the halos of dark matter around galaxies. Almost certainly they must have, because, galaxies are everywhere. So one of the things we're beginning to search for now is the effects of passing through a dark matter halo on a gravitational waveform. This is another example of what we mentioned before. It's called gravitational lensing. So gravitational lensing of gravitational waves hasn't been seen yet, but we're searching for it. And if we find evidence that gravitational waves from some source are lensed, then the chances are they will have been lensed by a dark matter halo. And that's great news because it allows us then to learn something about the distribution of matter in the dark matter halo. Now, we can do that using light a bit. Maybe your students know we can measure the rotation curves of galaxies, and that gives us evidence that the dark matter exists. But probing the dark matter using gravitational waves would be really useful as well. And that would be, we think, maybe possible within about 5 years. Can't promise, but certainly as we see deeper into the universe, the chances of detecting a lensed gravitational wave signal should increase.
Thank you, sir. We have another question. So how can we feel the gravitational wave?
Well, we said near the beginning that the effects are incredibly tiny. So as a result, you really wouldn't feel it at all. Even if the black holes were at the distance of the sun, you know, believe me, it would not be a good thing for the Earth if we were so close to a pair of black holes, because the gravitational field would be very strong and evolving and changing very fast. But the gravitational waves produced by that, by the time they reached us, would still produce a disturbance of only about 1 nanometer, 1 billionth of a meter. So you would really not notice. You know, there are other physical consequences of being so close to a pair of black holes that would be dangerous. For example, there could be what we call an accretion disk around the black holes that could be emitting strong amounts of X-ray radiation. That's what would be harmful, but the gravitational waves really wouldn't produce any harmful effects at all. The only time those would start to get a problem is if you really got to about the distance of the event horizon of the black holes. But frankly, there you would have other things to worry about than just gravitational waves.
Thank you, sir, for your nice answer. So we have another 2 questions. So first one, can we polarize gravitational waves just like electromagnetic waves?
Well, gravitational waves are polarized, and I didn't get time to mention that, but there are 2 polarization states of gravitational waves, and the angle between the polarization states is not 90 degrees like it is for light. You know, electromagnetic radiation, you have the polarizations can be like, you know, up, down, or right, left. The polarization states are at 45 degrees to each other. And actually, on a very deep level, just to connect it to an earlier question, this tells us something about the quantization of the gravitational field. It tells us about the number of spin states of the graviton, if it exists. That's a kind of side question, but just if we ask ourselves, what are the polarizations? Well, nature, when it produces a gravitational wave signal, imprints on that gravitational wave signal a polarization state. That will be determined by the orientation of the 2 neutron stars or black holes when they're orbiting each other, things like that. The catch, however, is we do not know how we could change that polarization state. We can do it for electromagnetic waves. We can use a polarizing filter. We can use a waveguide. We can use, you know, for radio, for light, and for other sorts of electromagnetic radiation, we can manipulate the waveform in that manner. But for gravitational waves, as I said before, because they are produced only by the most massive and violent cosmic events, we don't know how to produce them or how to manipulate them. So we don't really know how we could do that. Again, like I said before, we should perhaps never rule this out. Maybe in the future we'll work out how to do it. But at the moment, we can't even imagine how you could change the polarization of a gravitational wave unless you can carry around a pair of black holes in your pocket.
Thank you, sir, for your nice answer. This may be the last question. So, can evidences of gravitational wave validate the string theory directly or indirectly?
Well, again, that's a fascinating question. It really deserves almost a whole seminar in itself. Let me just note a couple of points. So, again, the really honest answer is we don't know for sure, because this is just the beginning of a new field and we need to explore ideas much more thoroughly before we can really determine what we might say and what we couldn't. But remember what we said about the graviton. We said that the energy scales associated with the graviton are such that right now we are not probing those energy scales. We're seeing much lower energy gravitational waves, and we don't see the effects of gravitons. If we wanted to see the effects of strings, then we would need to probe to even higher energy scales. So directly seeing the effects on the waveforms, I don't immediately see any way that would work. However, there's one very important caveat I should add. One of the things about string theory is that it allows, in principle, the existence of universes with higher numbers of spatial dimensions. But if our universe did have a higher number of spatial dimensions, then you could imagine it possible that gravity propagates through those extra dimensions, whereas the other interactions like electromagnetic waves do not. So there's a lot of work on this, what are called brain world models, where gravity propagates through those extra dimensions, the bulk, but the other forces can only propagate on a smaller dimensional subspace called the brane, B-R-A-N-E. So there has already been some work to look at how we might use gravitational wave measurements to test some of these brain world models. So let me mention just one way that this might work. If you have a signal coming from, let's say, a pair of neutron stars, and the gravitational waves propagate from that, and they can propagate through the extra dimensions, then the strength of the gravitational wave signal as a function of distance will vary differently from the strength of the electromagnetic signal as a function of distance. So what that would mean is there would be an apparent mismatch between the distance you deduce from gravity, assuming 4 dimensions of space-time, and the distance you assume from light, because the gravity can use the extra dimensions to propagate, the light cannot. So the binary neutron star we observed in 2017 was relatively nearby, but that analysis was done. We looked at the distance deduced in light, and we compared it with the distance deduced from gravitational waves. And if they had differed by a lot, that would already have been a hint that there are these extra space-time dimensions consistent with some of the flavors of string theory. Now, we didn't see that, but maybe that's because the space-time scale on which those extra dimensions become important is much larger than the distance to the neutron star merger. So we cannot rule out yet that those extra dimensions exist, but we can just rule out that they exist on small scales. Small is a relative term of about 100 million light years. So we want to keep doing this test in the future so that we can rule out, or maybe not rule out, those higher dimensional spacetimes. So in fact, one of my most recent papers was with a student working on how LISA might be able to do this in the future. But we need to wait until LISA observes black hole mergers in the 2030s, because it will observe them much, much further away. So we will be putting stronger constraints on the existence or not of these higher dimensional spacetimes.
Thank you,
that
sir.
was such a good question to end on.
Yeah. So we should conclude our discussion session as there is no more question. So thank you for your wonderful presentation and exciting discussion session, sir. I think the students have learned a lot of things, new things by your presentation and discussion session. So we would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, sir. So we have organized this program to motivate and encourage our students in this corona pandemic situation, and we are very grateful to you that you have accepted our invitation for our students. So hopefully in near future, we'll arrange another webinar with you, sir. So thanks again.
Wonderful. It's been my pleasure, and thank you very much to everyone for their wonderful questions. I hope I answered them well. And yes, I look forward to joining you again in the future. Thank you very much.
Yeah, bye for today, sir. Bye. Goodbye.